Welcome to Maths with EJD. I've been talking about extensive form games, and in the first video on that, we looked at the concept itself that it is actually a scenario where we have players making sequential decisions. And the video after that, I looked at game trees and nodes, which is a very nice way of representing extensive form games. So here we'll be looking at Subgame Perfect Nash Equilibrium. Okay, and we'll be considering the same kind of scenario I started with from the very first video, splitting $100 between player A and player B and how they go about that. Okay, so what's the definition of SPNE? That's subgame perfect Nash equilibrium. So um, a subgame perfect Nash equilibrium. Feel free to call that SPNE. A subgame perfect Nash equilibrium uh, is a refinement. It's actually a refinement of Nash equilibrium for extensive form games. Of course, extensive form games are more like sequential games, extensive form games. Okay. It ensures that strategies constitute a Nash equilibrium in every subgame. Okay. Of course, we already know the idea of a Nash equilibrium is that situation in a game where the payoffs of the players involved cannot be improved, no matter what the other player does. All right. So let's look at the steps to find SPNE. Steps to find SPNE. Uh, Subgame perfect Nash equilibrium. What are the steps? First one is to identify all subgames. Okay. Then after that, you solve each subgame, each solve subgame, solve each subgame using Nash equilibrium. Then afterwards, you can combine solutions to form the subgame perfect Nash equilibrium. All right. So let's look at an example of this. Example, like I said, we'll be considering the same scenario we started with when we started talking about extensive form games. So the scenario is such that we have, uh, imagine we have two players, two players, A and B, actually decide how to split $100. Okay, so player A chooses between splitting fairly, and that will mean get each person get $50, so $50 each, or 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 unfairly. Unfairly would mean that $90 would mean $90 for A and $10 for B. That is what unfairly would mean. Then, if A chooses unfairly, that's where the real game is. If A chooses unfairly, If A chooses unfairly, B can accept or reject the split. And then there's one more thing. If rejected, if rejected, both get nothing. Both get $0. Okay, so that's how that goes. Now, um how does that play into the current into SPNE, so Subgame Perfect Nash Equilibrium? How does it play into it? Let's see that. So, um, number one, can we look at the sub games? We have the sub games. We have sub game one. Sub game one is where the where player B decides after after player B decides, right? After player A chooses unfair. After player A chooses unfair. That's the sub game one. Now, how do we solve this sub game now? So that's the second next step. Number two, then we solve sub game one. Okay. So here now, if player B, if player B accepts, if player B accepts, then payoff would be 90-10. But if player if player B rejects, payoff will be 0-0, like we know already. Payoff will be 0-0. All right. Then the last thing will be the solution is such that, it's better to get $10 than to get nothing, right? So most likely player B prefers accept because $10 is better than $0. Though he's been cheated, but then it doesn't matter. I mean, it's better off than getting nothing. So then the third step is to now combine the strategies. So combine strategies. So in combining strategies, right? And that will be anticipating B's choice. Okay. Player A chooses unfair. Player A chooses unfair because player A already knows that player B would prefer to go home with $10 than to get nothing. He would rather instead of playing fair, player A would play unfair because I mean he can already preempt that player B won't mind going home with $10 instead of going home with $0. So player A chooses unfair for payoff 90-10. Okay. Having preempted what player B might do. So to show that in a game tree, like we did previously, to show this in a game tree now, again, we have player A has two options, either be fair or be unfair. Okay. So if it's fair, that's 50-50. Then if it's unfair, player B is confronted with two choices. So player B now can now accept the player B can accept or reject. Okay, if player B accepts, that will be 90-10. So A gets 90, player A gets 90, and player B gets 10. If player B rejects, that'll be 0-0. So we know nature, I mean, for a rational player, right? I mean, I think that's really important to emphasize. For a rational player, A rational player would rather go with $10 than to go with $0, and that is why the combination of sub the sub game perfect Nash equilibrium is going to be like, because player A knows that player B would accept 10 instead of 0, then he would play fair. He would play unfair rather. Um so we have this. So player A plays unfair, and then at the end of the day, player B accepts. And that's so at the end of the day, the this sub game perfect Nash equilibrium will be 90-100. Okay, that is it in the game tree. Well, which we can also represent in which you can represent as a matrix. So let's do the matrix representation. So for the matrix representation, okay, we have um we have this, right? So uh player A can be fair or unfair. Player B can accept or reject. Now this is player A and this is player B. So if player A is fair, sorry, it should be the other way around. This is player A and this is player B. So if player A is fair, no issues. We just have 50-50. So whatever 50-50, that is fixed. Then if player A is unfair and player B accepts, that's 90-10. Then if player B rejects, that'll be 0-0. Now, if you look at all of this, right? Um, so by what we have concluded in the talking about the game tree, you discover that this portion seems to be the Nash equilibrium for the game, for the sub-game perfect Nash equilibrium. This is it right here. Uh, because so player B's best strategy is getting 90, and player A's best, although the best strategy would have been 90, would have been 50, right? Would have been to end up getting 50. But because uh, player B is at the mercy of player A, then at the end of the day, if you combine both strategies, this is going to end up being uh, this is going to end up being the sub-game perfect Nash equilibrium. Okay, so that is how that is. So that is how that is going to be. And that's it. So in the long run, right, we just know that the SPNE strategy, so SPNE strategy at the end of the day would be that player A will be unfair and player B would accept. Okay, so that's the sub-game perfect Nash equilibrium strategy. And that ends this particular video. In the next video, I'll still be talking about something related to extensive form games, and that would be backward induction. And that's still so using still the same scenario. I'll be explaining the concept of backward induction from that. So that is how it's been today with in this video with sub game perfect Nash equilibrium. So watch out for the next video on backward induction, still on extensive form games. If you have not subscribed to the channel, this is a good time to do that. And you also want to hit the notification bell so you can get alerted each time a video is released. And of course, you want to comment to let me know if there's a topic you'd like me to teach or it's a problem you want me to solve. Then you can also like and share so that more people can have access to this great content. Till I come your way again, keep playing the game of life with wisdom. Bye.